Okay, so in this video, I'm going to talk about the second derivative test. It's maybe slightly oddly located in our textbook because the second derivative test relates to material we've already covered. The second derivative test relates to local extrema. So suppose we have a problem where we're trying to find and classify local extrema. And we found C, and the first derivative at C equals 0. Um, so C is a critical value. You can also have critical values where the first derivative doesn't exist, but I'm intentionally only looking at critical values of this form, where the first derivative equals 0. So this might be a local extrema or it might not. The first derivative test involves creating a sign chart. And for example, if we go from positive to negative, then C is a local max. Whereas if we go from a negative to negative, C is nothing. I mean, just that is to say, it's not a local max or a local min. So we can classify C. The second derivative test gives us another method of classifying C using the second derivative. It is aptly named. If the second derivative at C is positive, C is a local min. If the second derivative at C is negative, C is a local max. And that's because if the second derivative is positive, we've got our concave up function, we've got our upright bool, and the critical value is the bottom of the bool. It's a local min. Whereas if the second derivative is negative, we're concave down, we've got our upside down bool, which has a local max. The third case is unfortunate. Because, I mean, what are the possibilities of a critical value? They can be a local min, a local max, or neither of those things. So you might expect greater than 0, local min, less than 0, local max, equals 0, neither of those things. In fact, if the second derivative equals 0, the test fails and we gain no info. Very, very sad. But that's the second derivative test. And The second derivative test requires you to take the second derivative, but the second derivative test can be useful because maybe you needed the second derivative anyway. Like maybe your problem is you've got a function f of x equals x cubed minus 2x squared plus x minus 2. And your goal with this function is to find local extrema and inflection points. Well, let's go. Let's start with let's sort of start with the local extrema. We have to take the first derivative before we take the second derivative. So f prime of x is 3x squared minus 4x plus 1. And this always exists. So as far as the local extrema go, we set it equal to 0 to get the critical values. And x is 4 plus or minus the square root of 16 minus 4 times 3 times 1, all divided by 6, 2 times 3. 4 plus or minus the square root of 16 minus 12 is 4. So 4 plus or minus 2, all divided by 6. So 1 and 1/3. And if we were using the first derivative test, we would now create a side chart. Okay. Instead of doing that, I'm going to use the second derivative test. And my rationale here is that if I want the inflection points, I need to find the second derivative anyway. F double prime is 6x minus 4. And since I have the second derivative anyway, I might as well use the second derivative test rather than create the sign chart. F double prime of 1 is 2, which is positive, so 1 is a local min. F double prime of 1/3 is -2, which is negative, so 1/3 is a local max. And now I go ahead and find the inflection point. I've sort of done what I wanted to do, so I'll just run through this real quick. We set 6x minus 4 equal to 0. It's 2/3. And the sign chart verifies that this is an inflection point. If they're not going to find the second derivative, there's probably no reason to use the second derivative test. You'd probably just use the first derivative test. But if they're going to find the second derivative anyway, it can save you a step or two.